So today we dig our hands more into different algorithmic ideas. Let me briefly recap where we are up to now, and then move on. We've seen so far we've seen whatever you might want to call Tikhonov regularization, penalized imperialist minimization, so on and so forth. The basic idea has been to consider the minimization of an empirical error defined by a given loss function and the data. Penalized by a suitable square norm of some reproducing kernel Hilbert space, which is chosen to be the function space we minimize over. Okay, that's the biggest possible class we can consider. We've seen that despite the potential infinite dimensional set of functions we are considering, the solution of this problem is can be always written by a finite combination of kernels at the training set points, the very source of what we might call non-parametrics. And then we moved on and say, okay, we know that, but how do you actually compute the coefficient of this expansion? And it turned out that this is an answer that cannot be answered unless you actually consider specific choices of the loss functions. So we then moved on and make some example. We reviewed logistic regression. It was kind of, we spent a little time on that. It's a very standard algorithm. The main reason why we spend a bit more time on that is essentially because it served us as a way to actually introduce hinge loss, which is kind of the SVM loss function. The idea there is that we kind of take a slightly different route. We start from the logistic loss. We consider, so let me call this whole thing E at lambda F. With a bit of abusing notation, I'm also going to consider the case where I'm going to use the same symbol to denote the case where the function is just a vector. So assume for a minute that my function f of x is just of the form w of x. This is a very generic. I made no assumption up to now. I'm just saying it's linear with respect to some feature map. It always exists for any reproducing kernel Hilbert space. And we consider for the logistic loss function this kind of functional. Okay, what is the idea? Well, this kind of iteration. So the idea is just to run gradient descent on the objective function because it's a linear problem in my variable. I don't have a closed form solution, but I can run this. It's just a basic algorithm. Blah 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 blah. If this feature map is finite dimensional, so if it's given by a finite dictionary, if it happens to be just a linear kernel, so this is just the identity, then this actually amounts to an actual algorithm that you can implement. If it so happens that this is an infinite dimensional feature map, then you cannot store infinite dimensional vectors, so you do have to use some kind of representation. And in this case, we show a ad hoc representer theorem that says that not only the minimizer of this function will satisfy a finite dimensional representative, but this iteration itself, and we show that there exists a vector Cti. Wt can actually be written in a specific form, and then it gives rise to a representer theorem for the gradient descent itself. So this is the usual representer. This is the face of the representer theorem. The key point here with respect to the general result about the minimizer is that Ct, not only we know that there are n coefficients, but we're actually telling you how to compute them through some iteration that looks very much like this. But now rather than d or infinitely many parameters, we just have to deal with n parameters. Okay? So this was the basic idea of how we did the logistic regression. I put the gamma t here, but we can really take just a constant step size for this specific case because it's a smooth loss. I don't give you the explicit form of this GT because it requires me a bit, but we derived it. Okay? So far so good. Any question about this? So this is the 5 minutes recap of logistic regression. Is also going to be the 5 minutes recap about SVM. Why? Because the route we take was basically saying what is the main difference between logistic and hinge loss is that the hinge loss is not differentiable. So we actually spent half an hour introducing the basic definition of a subgradient that allows us to generalize the optimality condition and the gradient descent algorithm. And what we obtained was, A, that we could actually get an idea why supervector machines are called supervector machines. Essentially, by imposing the optimality condition through the subgradient, we get that not all coefficients might be different from zero, might be different from zero, or in other words, some of the coefficients in this expansion might actually be exactly zero. And then we introduced a way to compute them through an iteration that looked very much like this. The only difference is that rather than having here the actual gradient, we'd have to replace this with an element of the subgradient. A thing that in general is a mess to compute, but in our case became extremely simple because we just apply chain and sum rule, and all we had to do was to take the left derivative of this loss function. Okay. What we obtained looked very much, well, not very much, it actually reminded a bit of the perceptron with a few differences, with an extra regularization, with some extra margin. Okay. But in some sense, the shape of the story was just the same, and we spent some time introducing, so I'm not going to throw it again. What we actually started doing last week is consider the specific case where rather than the hinge or logistic loss, we consider least squares. In this case, we have the same story. We have the W satisfies now a linear system. What is X? X is the N, so let me write this. So phi is a feature map that goes into F. And let's say for a minute that F R to the P, then N is a matrix which is N by P. And basically the rows of this matrix are just phi x1, phi xn. Okay. So or if you want just to consider, if you want to just consider the linear functions, okay? So in which case this is just the input space, which is say RD, and this is just the output space, which is the feature space, which is the identical thing to the input. So it's just RD again. So this is just the notation for the data matrix, okay? In that case, this is an N by D matrix, which is the data matrix. Each row is an example. Each column is a feature or a variable. Okay? So this matrix is N by D. If instead of using features, if instead of using the linear function, you use a finite dimensional feature map. So you use linear function over, say, a finite dictionary or something of this form, where the feature space is finite dimensional. This is going to be the element of the input mapped through this feature. So each of these is going to be, again, N rows, one per example, but you're going to have P columns, one per feature. Okay? Make sense? Presentation clear? Y hat here is just a collection of the outputs. Take all the outputs and I stack them together. This is just it's useful to use this notation for the least squares just because it's more compact. Okay. How did we derive this? It's particularly easy because in this case, if you plug the square loss, the key point here is that for the square loss, the linear case, this thing here can be written as hex hat W minus Y hat, and this is, okay? And again, strictly speaking, whenever you do this complete identification between W and F, it works in the case where phi, the connection between W and F is 1-to-1. Okay, as I told you, this is not always the case, but this thing works no matter what the result is correct up to some technical difficult, enhancement in the proof. So fair enough, for understanding purposes, this is okay. I'm making a simplifying assumption, but you don't really see the effect or the problem with that. Anyway, this is the special case when you consider the square loss. If you want, you should put 1 over n. the gradient, set it equal to 0. You have a square here, a square there. They go away. You get the linear system, and that's what you get. Where you get this equation. Okay. Then we somewhat, this was kind of the very end. We rushed a bit into this one equation, and we said, okay, can I do the same game I did before? Let me call f lambda. Let's call this guy w lambda. Again, you can use the representer theorem, plug it in here, derive, set the condition to 0, or we can just directly have an alternative form of that solution. What do you do? You basically show that this particular w lambda here always satisfy this equality. So again, there is a representation of this one solution, and this was given by the following expression. Again, this one you get just because you set everything equal to 0, and this one you get how? Anybody remember? How do we get this one expression here? Right? Tell me that was the second step. The first step is what? You use this with decomposition. How? What was the basic trick we used? Yeah, where do you use it, SVD? On what? So I guess if I have to, if somebody asks me to give a sketch of the proof, which is what I did last time, I was basically saying, you know, the proof of going from here to here was the usual thing. First, we realized that in the linear case, writing this is the same as asking w hat to be of the form x hat c lambda. This is the first step. Again, we've did it at this point, you've seen this at least 3 times, if not 4. Asking this or asking this is the same thing. Okay, so that's the first thing. And then what you do, you prove that this guy actually satisfies this equation. Okay, how do you do that? You basically, the trick was you use SVD to prove what? To prove that you can basically take this X transpose and move it in front of here, but then you have to swap the order of these 2 matrices. And if you put these 2 steps together, that's what you get. So the first thing is not a proof of anything, it's just a restatement. Proving this is the same as proving this. And then you prove this. How? Just linear algebra. You take this X transpose, you move it in front, you swap the order, and you use SVD to do that. Use SVD how? Literally, you take the SVD of X, and you plug it in every place where you see X. And then you check that you get an identity. Okay? So the identity you need to prove is this following matrix identity. Okay? So X transpose, I move it in front of the order inside. If once you know how to prove this, that's basically what leads to that result. Okay? But that's nothing specific. Any kernel can be written that way. He's asking this equality. What am I using in here? Again, a thing that we've been discussing for 3 days, so that's why I'm a bit quick about it, which is the relation between kernel and feature maps, which is the fact that any kernel can be written this way. Okay. The key point is that sometimes I'm using, so in this reasoning, phi plays a different role whether it is finite dimensional or infinite dimensional. In the finite dimensional case, phi is an actually useful computational object. You can use it, okay? You can use it to build this matrix, build it and use it and invert it, or you do gradient descent in logistic case and so on and so forth. Phi is infinite dimensional is absolutely useless from a practical point of view, but it's useful just to do a mathematical manipulation. How? Like this way. Somewhat, ignore its infinite dimensionality for a while, and you just treat it for a vector. You just do from W to C, and then to realize that once you are to C, you don't need phi at all anymore. You only need the kernel. Okay? That's the way we've been doing things for logistic, hinge, and now for if it's finite dimensional, I use it. If not, I ignore the fact that it's not. I sweat a little bit to massage it until I get some expression like this. Check what is this. This is just a matrix, which is now n by n, and it's just a matrix when I take inner product of all the points. So this is as long as you can compute this expression, even though this is infinite dimensional, this phi is infinite dimensional, you're good to go, because that's all you need. Okay. So anyway, so this was just a recap of the proof, which is really one line, and this is where we get to time. And the last point is exactly the fact that this, again, you can just look at this as the finite dimensional case for linear kernels. This expression holds for, you can use it for any finite dimensional feature map if the feature map corresponds to an infinite dimensional space. So then you will use this one here instead, where this matrix become the kernel matrix. Is the matrix whose entries are kxi, kxj. And of course, this you can compute for any time you have a kernel. Okay, so this is kind of a recap of least squares. Any question about this? There's nothing computational in that reasoning, okay? No. You can do anything when you have infinite dimensional stuff. You don't even allow but you talk about it and write it on paper. So, as I said, phi in the infinite dimensional case is not a computational. It is not some operation you do. It's a proof. It's a proofing technique. Can you write down? So now the question becomes: can I just write down? If this matrix is n by infinite, do I have a notion of SVD? Yes. Okay. It's just the same. It's actually just the same. It's called the singular value decomposition. It becomes an operator, but it's the same. Okay, and so that becomes just a step in the proof that you can still do, and then you end up doing something that doesn't use an infinite dimensional feature vector. Make sense? Here, yes. Okay, so let's make a couple of remarks, and then we move on to do something cool. So first thing is, let's just make a couple of remarks. First thing is, if D is more than N, what is the complexity of that algorithm over there? Let's check. I have to invert, so I have two choices, okay? I can work here or here. Let's just check what is the cost of doing this. What you have to do. You have to invert the matrix, which is D by D, okay? And again, roughly speaking, from a numerical analysis point of view, this is typically the cost of an inversion, when it's considered to be roughly how much? Go cubic with the side of the matrix, okay? Rough estimate. Okay, so, and that seems to be the main complexity there, but it's weird, right? Because the number of points should enter somewhere. If I give you 10 points, 10 dimension and 2 gazillion points, is that possible that I only have, no, so there's something we're forgetting. So where is it? That transpose? Yeah, all the multiplication, all of them, you have to do them, okay? So once you have to do them, it means that you have to compute some stuff. For example, the X transpose X, this is going to cost us a bunch. How much? Well, let's see. I have Sorry, I have P, so I have X transpose X, which means that I have to take the transpose of X. So I have P vectors of size n, and I have to multiply by other P vectors of size n. Okay, so each multiplication is going to cost me n. I have to multiply n numbers, and then I have P against P, so it's going to be P squared, so or D squared. I use D or P, doesn't matter. Let's put P. Okay. This is the order of magnitude of the cost in terms of time complexity. What about space? What is the biggest thing I have to store? Okay. Agree? Let's assume for a minute that the feature map is finite dimensional. What is the cost of computing the one below? This guy. It's basically the same thing I wrote, but you have to swap n and p. Okay, so you get n cubed plus p n squared. Okay, and now the cost of, let's check a second, okay? So the cost of these would be if you have a really finite dimension. Okay, so assume for a minute that dimensions are finite, and I tell you p is smaller than n. Which one would you want to choose of these? First line, I just get a linear dependence on the big guy, and then I have to pay cubic on the second one, but whatever. I mean, suppose that now I tell you that p is actually bigger than n. Then immediately we want to swap to this guy. Okay? Suppose that now that p is actually infinite. What happens? Well, n cube is still going to be there. This pn squared becomes what? I have to compute, this pn squared was coming from this, right? I have n vectors, I other n vectors, and I counted the inner product between them, counted p. Generally, it would be just the cost of computing the kernel matrix between two vectors, okay? Which is going to be, let me put here, is going to be something. So in this case, it's going to be something like n cubed plus ck squared. What do I mean by ck? Is the constant, is the cost of evaluating the kernel at any 2 points, which typically might depend on something like the dimension of the input or whatever is the input, in fact. But it's whatever is this ck standing for, okay? The cost of computing this, and I have to do it n squared times. Agree? Then I have to store something in memory. What do I have to store? Well, this. I'm going to take the data, I'm going to compute this guy, and that's all I have to store. So I actually go to this. Okay? Fair enough? Makes sense. P has to disappear. I have to be able to make P disappear if I want to be able to really do non-parametrics. Is this it? Is this the complexity of the method? Kind of. Any question about this? I'm just taking the rule of the game is 2 numbers, multiply counts 1, and then just count how many multiplication I do. And in the case of inversion, I assign to it a rough cubic dependence on the size of the matrix. Again, yes, it depends a bit here too, you mean? Yeah. You can, again, it depends a bit how you want to, you can upload the whole X in memory and then compute or do it on the fly. And it depends a bit. I wanted to take care of the linear case and the feature space case in one same line, and that's why it's a bit rough. The main point of this story, if you want, is this guy or this guy, okay? Yeah, anything else? So basically, the story here is if P and N, well, N is always finite. If P is finite, I can always choose whichever equation gives me faster computations. If P is infinite, if I really want to go non-parameters, I have to go below, and that's it. Okay? Now, there is something to keep in mind, which is we haven't discussed how to choose lambda ever, but you have to choose it. Okay? And again, there is going to be theoretical stuff to do to tell what is optimal and what you can do, but it's also typically some computation that you have to do. And typically, it's something where the rule of the game goes like this. First remark about computational complex. The second remark is about what we call regularization path. Basically, the idea here is that when you actually look at the real computation that you have to do when you solve a problem, is compute this solution for many values of lambda, and then one of the values of lambda by checking how good is this solution in some sense. Okay? Cross-validation, marginalized likelihood, complexity regularization. You open the book of your favorite statistical procedure to choose lambda. They all take in input a sequence of W lambda, or F lambda, whatever you want to call it, and then return one according to some criteria, which is not the topic of this discussion. The topic of this discussion is just to point out that you never have to compute just one lambda, okay? Almost never. You typically have to compute a bunch, and then you have to pick one, okay? So this idea of computing not one value, but all the values that correspond to different regularization levels is what you call sometimes the regularization path, okay? It's the path of possible solution you obtain by moving lambda and obtaining solutions that correspond to different regularization levels. That's typically the important quantity to compute, okay? And here what you see is that if you just, how do you solve this linear system? Well, this is a nice symmetric positive definite matrix, and if I just give you a lambda, the typical way you want to go is something like Cholesky decomposition. If you then, and then you get complexity like this, but then if you have to compute this thing for many lambdas, you will have to multiply this complexity for the number of lambdas you want to try, okay? So everything here gets multiplied by the number of lambdas. Depending on how many models, how many lambdas you want to try, this might increase the computation dramatically. Notice that you could say, is there a way to avoid this? Is there a way to avoid having to solve this problem for any lambda you want to try? You know of a way to solve this linear system in such a way that in some sense you do some computation first, and then you can get the solution that corresponds to all lambdas more or less for free. How would you do that? Is the question clear? Option one, I do Cholesky or Cholesky, I never know how to pronounce it, but then once you've done it again and again and again for every lambda. And you don't really reuse the computation, you just do it every time from scratch. But suppose that you already know that you want to compute them all, what would you do? Well, one thing that you could do is to actually compute the eigendecomposition of the matrix. Okay, you just do the eigendecomposition once and for all. And then once you have the eigendecomposition, you can compute all the inverses. Okay, so basically the idea here is x transpose x, or rather xx transpose is going to be to u sigma u transpose. And doing this operation costs n cube. Okay, once you've done this, suppose that I ask you, okay, now compute this. Well, yeah. What do you have to do? You just take u that you already computed. Now you're really computing stuff using this, okay? And then you take this sigma, and basically you do sigma plus identity, well, n if you want, to the -1. So all the operation you see on the matrix, you have to just do now on the diagonal. So that's trivial, it costs you nothing. And then you have to just push everything back together. But as again, it's just multiplying things for something, this multiplication costs n cube. Okay, they're typically going to be n squared like operations. Because it's like a matrix for a vector, essentially a vector, this is a diagonal matrix, and then again. So in principle, if you know that you want to solve this system once and for all, what you could do is to do the eigendecomposition once, pay an n cube, and then just compute all this stuff for any lambda. So this is way 2 to make this computation. If you try to do this in practice, if you see this the first time, you're like, oh, okay, so first of all, people hate SVD because it's super slow, but this actually looks like a reasonable idea, okay? Because if instead of computing one solution, you want to compute a bunch at once, this seems okay. The truth is that the constant here, this O and this O here actually hides very different constant. The constant here is really big, okay? Whereas the constant there is not so big. And so the rule of thumb is essentially that if you want to try a number of values which is not too big, say 5, 10, 20, this complexity might still be better than going this way. If you want to really compute many, maybe this is the better way to go. So if you want to be very careful in choosing lambda, you want to try 1,000 different parameters, well, maybe then you can go this way. Okay? Where does this lead us? To the next thing, which is all this story basically points us to the fact that we design a learning principle. We look at the computation, and then we see that depending on different regime and what we want to do, we have these different computational costs. And the second and the last point shows that whenever we think again that we're not just solving numerical, but we're doing machine learning, so at some point we do have to choose a model, we do have to tune parameters, then the way we want to measure the computational cost changes a little bit, okay? If you're a numerical analyst or optimization guy, you just look at the problem and say, okay, this is the cost. When you go back to machine learning, like, oh, no, I still have to choose lambda, so this is the new kind of computation I have. So the discussion we want to do next is somewhat going in the direction of fixing some of these and introducing something completely new, a new way of thinking about designing learning algorithms. We're going to stick to least squares, although pretty much everything I said holds for other loss functions and also for other kind of algorithms, in the sense I want to show you now. Let's consider the following thing. Wt plus 1 equal Wt minus gamma at W minus y hat. Okay? What is this? Gradient descent of what? Of the square loss without any penalty, though, with lambda equal to 0. Okay? If you want, this is the same as if I could solve least squares with gradient descent too now, but now I put lambda equal to 0. Suppose that now I tell you that this is a fantastic algorithm. Okay? This is my favorite algorithm in the world. And no, I put x hat there as if it was just a linear case, but it's like any nonlinear feature map. Okay? Does this iteration make sense or not? I want to use, you give me data, I'm going to run this. Is this a good idea or not? You should immediately say no, okay? You know, if you don't think too much about it, you say, no, it's a bad idea. Why? Yep. No, forget about computation. Just from a learning, we're going to look at computation in a minute. But just think in terms of design principles of an algorithm. I give you this and I tell you, I want to use this. Does it make sense from a learning perspective? Or would you want to change it somehow? We did something weird, right? We took the guy over there, we did gradient descent, and we put lambda equal to 0. This whole course is about thinking about how you can avoid overfitting or at least control the way you search for solutions. Is this guy looking for a good solution or not? Unclear, right? If you let the number of iterations go to infinity, you're going to fit the data. Right? That's all you're going to do. If your feature map is very simple, you're probably not going to fit the data, but then you're basically regularizing because you take too simple of a model. But if you're in a high-dimensional case, your feature map is complicated, then you do have that if t goes to infinity, this just goes straight to a regularizer of the empirical risk. Yet is my favorite algorithm. Why would it be possible for this to be a good idea? Well, one way to think about this is to say, okay, let's see if we have 3 parameters that could do something interesting for us. For example, how many free parameters I have in this computation? W, you mean? Yeah, W, so he's saying that the free parameters are the W. Yes, but this I tell you how to compute them, okay? I mean free hyperparameters, let's say. Parameters that you have to choose before you run that. You get the data, the step size, and iterations, okay? Are this doing any good to us? The point of view we're going to take is we're going to assume basically to take gamma so that the thing converges. We're going to rediscover why there is a good value for that. And we're just going to wonder if number of iteration is doing something. So let me just do a plot first. Suppose we're doing a finite dimensional problem. Okay, so this is x and y. And these are a bunch of points. Suppose that I took a feature map which is, gives me a space of function which is complicated enough, okay, not the linear function. Some even finite dimensional one, but say sine and cosine in this one dimensional case. I start from w equals 0. Now the vector of zeros, and then I run that iteration. What's going to happen? I want to draw the corresponding solution, okay? So I run that, and then I plot f of x for a bunch of x's. What do I get? What do you think? At the beginning, you're going to get something relatively simple. And then the guy is trying to fit the data, okay? So it's going to keep on going, and it's going to try to fit the data, try to fit the data. So it's going to go up, then point, okay? These curves are different timestamps, okay? This is t equals 0, this is t equal whatever, 10, t equal 100, and I don't know, keep on going, okay? Let's ask the question again. Would you want to use this algorithm or not? No? Anybody want to buy it? You're going to buy it in the end of this class, but whether you like it or not. Like maybe if you don't go to convergence, what he's saying is maybe we shouldn't go to convergence. Maybe we should stop before. Maybe the stopping time is regularizing. Maybe the stopping time is doing something like what lambda does. Okay? When I pick a small lambda, I'm fitting. When I pick a big lambda, I'm not fitting anything. Here, if I have to guess from this picture, I would say t is roughly like 1 over lambda. Maybe not exactly linear or inverse proportional. Maybe there is some power, but qualitatively speaking, they should go one in the opposite direction of the other. If t is very small, I'm not fitting anything. If t is very large, I'm fitting the data perfectly. Okay? Now we can ask two questions. Okay? One, is this just a story, or can we convince ourselves that it's actually a meaningful algorithm? Two, what do we gain out of doing this? Let's answer the second question first. If it's really true, if it was really true that I could use the number of iterations as the regularization parameter, I would have an iteration that cost me the same as that. But now I have something really nice happening, which is that the number of steps I need depends not just on the rough amount of the data, but on actually how hard or easy is the problem. Because the stopping time is the one that you choose by cross-validation or whatever. This is kind of really a shift in perspective, right? All of a sudden, if I look at this complexity only depends on how easy on how big is my data. There's nothing about this, there's nothing about this that concern how easy or complicated is the learning problem. Whereas ideally, it would feel very nice to have a method that says, look, my data are horrible. I can do nothing with this. So I'm going to start to do some operation. And when I realize it's not very good, I just stop. Or I say, no, these data are awesome. I should really, really get the most out of them because I can really do the job. So I'm going to do more. Okay, this guy doesn't do that, right? If really you can prove that t is something like 1 over lambda, is doing that for us. Because the time complexity is going to depend on how easy or complicated is the problem. Okay? If the data are interesting, I'm going to fit them more. If the data are not interesting, if there is noise, I'm going to say stop it. Okay? So it's a pretty interesting promise. Okay? All of a sudden, rather than having your split brain in the statistician optimization guy, they cannot converge in this perspective where while the very nature of optimization is providing you a form to control the statistical complexity of your model. Okay? Again, I'm just announcing what would be nice to have, and it's going to be true, okay? But that's why this point of view is kind of interesting, because you would easily be able to take computational aspects and statistical aspect at once, at least for now, the time aspect of the problem. Notice that because if t was 1 over lambda, then I would actually be automatically computing the regularization path while I run my algorithm. Every step I take, I'm just considering a more complicated, potentially more complicated solution, one that can fit more. Okay? So at this point, you have a certain sense of expectation. Why the hell would this be a good idea? Can we prove that this is actually a good idea? How do we prove that this algorithm is a good idea, despite the fact that we put lambda equal to 0? And what we're going to see is that for the square loss, and that's why we start here, we're basically going to show that it is in spirit. It looks very much like, we're going to show that that iteration is providing us something that looks very much like this, where the in spirit is doing the same thing. Is inverting a matrix in a stable way. This is the way we're going to explain this guy. Okay? Yeah. It will. In general, will depend on it. So all this discussion I'm going to have simplifies for now, and I'm just going to say that I take 0, and everything I do works for 0. And at some point, I might point out what the effect of a different initialization strategy. 0 is good enough, and that's what I'm going to choose. Yes. Why? So first of all, I mean, for now, I mean a little less like this. I just mean, say, t small, roughly lambda big, and t big, roughly lambda small. Okay, not exactly a 1 over dependence. And why do I say this? Just if I look at this plot, it looks like I start from something simple. So when t is small, I get something simple. I start from 0, and I just I typically get something that is not too complicated. And then as I let t go larger, I'm going to fit the data. And so I actually allow my solution to eventually become more complicated. This is kind of a drawing version of a simulation that you could do on the laptop in more or less seconds. That's what that algorithm is doing, is descending that objective function. It starts from 0, and every step it fits more and more and more and more. And so if I start from something simple, I'm going to try to get something more complicated that fit my data. Does that make sense? This is just the qualitative statement. No. So what he's asking is, what if I don't need to regularize? Then don't do it. Okay? So if but here you would have to know that not regularizing here, if this story is correct, okay, and we should start pretty soon to show why this is correct before. But if this story is correct, you just say, well, just go, just keep on fitting. Okay. If your model is simple enough, you want to put lambda to 0 roughly, which means that you can just let t equal to infinity. Okay. Are we ready? Let's do it. So clearly I can rewrite this guy like this. If you actually play with this and just do a couple of, you just write down a couple of iterations, you start to see that you can actually write the iteration wt in closed form with respect to the initial iteration. Okay, this is a simple recursive expression, and you can just write down wt in closed form, and it's going to look like this: sum j from 0 to t minus 1 identity minus x hat transpose the magic. Again, how do you do this? Nothing. There is a basic recursive expression that says that once you have this, if you start from 0, you can write this down. Or if you don't want to just believe this, you just say, OK, let me just check this by induction. And it's one line. OK? So we're not going to do this because it's very simple. This is awesome. Why? Well, x was a number. I'm going to assume for this discussion that x transpose x is invertible. Okay? I want to make the discussion a little easier. And actually, what happens otherwise. So then we can say, remember a few facts, which are, if I give you a number, how much is this? If a is more than 1. Right? If instead of doing this, I actually consider the sum, it's going to be equal to 1 minus at. 1 minus a. Okay? That this equation holds if instead of a number, you replace the number with a matrix. In our case, particular symmetric positive definite matrix with norms smaller than 1. Okay? So take A and replace it with the matrix A with the norm smaller than 1. You can rewrite everything I wrote in that case. Okay? Basically get identity instead of 1. Okay? And a similar expression for that. It's a fact. That's called the Neumann series for matrices. Okay? Whatever. We don't want to do this for this case. We actually want to do this other kind of. Okay? We want to. I will actually do this kind of, you see, what I wrote up there doesn't quite look, I mean, the particular matrix I'm taking to a power is actually something that looks like identity minus something, right? So let me do it here. What do I get? B to the minus 1. Assuming you can get the inverse, okay? That's not the main point to work. I could put the pseudo inverse, the Moore-Penrose inverse with the no fact, but the cool thing is just this idea that when you're considering that, okay, you actually consider a truncated power of expansion that sorry, I'm just taking, for now I'm just taking it going a full expansion. And basically we're saying we start to get the feeling that maybe what we're doing there is doing something like taking a power expansion of an inverse. Okay? That seems like what we're doing. For our specific K, B, or if you want A, B is going to be X hat transpose X gamma, I guess. All right? And I shoved into the gamma somehow. I'm going to be sloppy about that. How do you get? Well, in here is so for, I mean, in here I'm just saying this. In here, well, it's a question for you. How do you get the thing that I minus b as a norm smaller than 1? Gamma such that that's true, okay? Fair enough. And if you do that, what do you know? Well, that series is going to converge, which means what? That this guy is going to converge. Okay? So we just provided a step-size choice that ensured the whole thing to make sense. And we also killed gamma as our potential regularization parameter. Gamma, at least for now, will disappear and it's just going to be a constant. So the only free parameter is the number of iterations. And you see, we're almost there. We're almost there. Because look, what was lambda doing here? It was taking an inverse that potentially, maybe I could also invert it, but then I would have to pay the maximum and a smaller eigenvalue, okay? I will have some instability property. Close to not invertible, then from a numerical point of view, what this method is doing, say, oh, I'll just put lambda, okay? So I make it invertible, and the more, again, here, you have, maximum eigenvalue. So let's call this, if you call x transpose x sigma, and let me call sigma max the biggest and smallest eigenvalue of that matrix. Then, if this guy is bad, then I might have a very unstable operation when I try to invert it. So when I actually add my plus lambda, I'm actually doing this. So far, lambda from, when we thought about it as a statistical parameter, we thought, oh, it's a budget on my model. And then from a numerical point of view, we're saying, oh, it's making my numerical inversion stable, okay? Here, we're discovering that you can actually ask the following question. Is there another way to make the numerical inversion stable? Is it a learning algorithm? And basically, that's the way we're taking, the route we're taking there. And notice it's kind of interesting because this opens, the book of how to solve a linear system is full of ways of taking stable inversions, okay? And this points at the fact that perhaps this will lead to learning algorithms. And indeed they do. So here, what do we know at this point? Well, we know that this is true. And so that if I take t, for now we know that if we take t equal to infinity, just to infinity, we basically do have the story that this smells like lambda equal to 0. If I take lambda equal to 0, what do I get? X transpose x to the minus 1. Okay? Lambda equal to 0 or t equal to infinity, I basically get that Wt is roughly x transpose x to the minus 1 x transpose y, okay? And same is W's lambda. They look the same, and they just go back to least squares. Just use your least squares. Again, assuming things are invertible. Okay. So this by just going through this matrix identities, we already kind of hopefully convince ourselves of this one here. Okay. It's not exact, but it's an argument very close to. No, so basically, so what he's asking is, what is the fact that X transpose actually is what allows us to get the pseudo inverse. Okay, so basically what I mean is, way. I'm assuming things are invertible because at that point I can just apply, because I don't have to, because this is more complicated than the one I wrote, and I'm just using that. The truth is that this is the one you use, okay? Dimension-wise, this is the correct one, is the real one, okay? And I'm basically showing that, because you can say, oh, but it's not invertible. Okay, it is doing more than is going to the pseudo inverse. Okay, this guy is the one that say, oh, if this is not invertible, I'm just going to take the eigenvalues, set the one that are small 0, I'm going to throw them away, and then invert what's left. That's the guy. That's basically what's going on. Okay, so this is the precise formulation I told you. And then you just take this measure and you apply to y, and you get what you get. Okay. Okay, so we're almost there. So what do we need to do now? Well, I just want to use this guy instead, okay? Because I want to check what happened t big, I can just go, asymptotically if you want. For t small, I really care about just looking at what happens when I take a finite sum. So does that make sense? And so what I get now is, so let's see, this should be identity minus gamma. Again, I just have to plug, I have to take A and put 1 minus B here and make everything matrices. Minus 1. Okay? Right? So this is actually inequality. So if you now look at this, okay, then you have X transpose Y if you want. What happens if you take t equal to 1? Take t equal to 1, what you get is that you get identity going away. This applies to its inverse. It goes away. So this whole thing is now is proportional to the identity. Okay, so for small t, you get something proportional to the identity. And that's exactly what you get when you put lambda very big. The term over there is dominated by the lambda. The X transpose X doesn't matter. You just get something proportional to the identity. Again, we found out that small t provides approximately what you're doing. What did we show? We show that from a numerical point of view, this algorithm is actually doing the same as that algorithm over there. And if you interpret what Tikhonov regularization does in the least square sense as a way to just find the stable inversion, we found another way. What did we get in the meantime? We got a way to actually do it in a computational efficient way. This is an equality, okay? Which one would you want to do computationally? You can just check. The first one, you just have to always do a matrix times a vector, okay? You take this. Every time you just do matrix vector, then you have a matrix times a vector, then you have a matrix times a vector, and so you always have operations that are linear in N and D, okay? If you actually go and try to do the same operation here, you have to form these matrices and then take powers, so you get something which is now quadratic or cubic, okay? So this is insane from a computational point of view. It's useful from a conceptual point of view, from a proving point of view, because we show now we are basically doing another form of Tikhonov regularization. Okay? But from a computational point of view, this is the way to go. And what is the complexity of this? Well, in time, so I'm going to replace this with NP. Okay? So I go down one order of magnitude and I add this lambda, because lambda is t, okay? The other way around. So here you have to compare this p cube np squared times lambda for npt. So you not only so think about it. I could even use gradient descent to solve that, and then I would have to do a full iteration all the way down to convergence for every value of lambda, and rather now we just do one iteration and we stop. How? That's a question to you. How do you stop? Well, whatever. What is the way you choose lambda? You do the same thing. Okay? You just do the same thing. The classical way of doing this is monitoring a validation error. And then we discover a classical effect. Suppose that you put here t. Okay? We want to check the behavior of E hat WT and EWT. what is the typical behavior you expect? EWT, E hat WT is just empirical error. As the number of iteration goes down, what do you see? Down. I don't know how fast, but it's gonna go down, right? I'm trying to, well, I know actually at least some upper and lower bounds on how fast. It's just gradient descent on the empirical. What about the expected risk? It's a new question if you want, right? If you're an optimization person, this is a new question. What is it? You know, I don't know. I was just doing a gradient descent for a reason. Now you tell me you're doing it for another reason. What's the story? Well, you're mixing them, okay? But up to this suggests that maybe the behavior is more something like this. At least in a worst case scenario where you have noise, you have a complicated problem, you're basically saying, what is the idea? That is at the beginning, it's gonna go in the right direction. And then at some point, it's going to turn and start to minimize the empirical risk. This is what is called semi-convergence. The idea that if you actually have an empirical problem, which is noisy, and you run an iterative optimization on it, the iteration itself, as what might call a self-regularizing or implicit regularization property, is actually a well-known fact, at least for linear problems. It's an observation that, to the best of my knowledge, was made around the mid-'80s in Russia by people like Polyak, Bakushinsky, and some of the big guys in inverse problem optimization. Just notice the following. Just take an empirical problem, okay, where it makes sense to talk about an exact solution, a noiseless solution, and then you can check what is the effect of optimizing. And the optimization is basically going to go to the right place for a while, and then turn to the wrong place. And then you can use optimization as a regularization device. And again, this is kind of an inspiring thought the first time you see it, because it just shifts the way you think about what you're doing when you're optimizing. Instead of just saying, I'm computing things to the best possible precision, you just say, no, I'm computing things. And that's just the way I build statistical models. So that's what's going on here. Semi-convergence refers exactly to this thing, that you go in the right place for a while, and then you go up. Okay? Notice that it also tells you, does it make sense? So let's stop a second and just recap the story, and then we make more comments and generalize this a little bit. This is basically the main story today. Okay. The idea is just we've been discussing for 2-3 lectures penalization as a way to design algorithm. I want to introduce a completely different way to design algorithm, which is just optimization of empirical objective functions. Of course, this is a statement that needs to be somewhat, refined a little bit. So I'm just giving you an instance first. I'm not giving you something super duper general, okay? And I'm taking the instance where I'm shooting for an optimization technique that actually is going to give me something comparable to least squares with L2 norm. Here I'm basically showing in which sense this can be seen to be true. The basic idea is that fitting will correspond to, that many iteration will correspond to overfit and few iteration with oversmoothing. Again, one way to go is just to do a simulation and convince yourself it's true. Another way to go is this is kind of the spectral way. We just use matrix identity and we look in terms of matrix expansion to convince yourself that this computation is actually performing a form of stable matrix inversion, where the amount of stability, the condition number, is now controlled by the number of iterations. Okay? And all is in these 3 lines, okay? And the key point is just this fact that the geometric series equality that you know for numbers, they do apply for matrices with bounded norms. Okay? We have a new way to think about algorithms. So that's in terms of what? So one thing, let me clarify. So the question is compare early stopping with choosing lambda by cross-validation. So let's first agree on one thing just to clarify the question. Using the stopping rule as regularization is not to be compared with cross-validation. It's to be compared with using lambdas. Okay, I'm not telling you how to stop. I'm just telling you that the iteration acts as lambda. So you don't use this as an alternative to cross-validation. You use this as an alternative to Tikhonov regularization, to least squares. You use cross-validation to decide where to stop. In fact, typically this plot in practice is you look at them. I'm running this on the data. I split the data in half. I use half as training set, and I optimize it. And then half to check the error. And I check what's happening on the second half. And I see that it goes down like this. And when I see that it starts to go, I mean, in real life, this goes down like this. Okay. I have to put a bit of a threshold and something to smooth out. But that's what happens. Okay. So that's an important bit. You know, iteration is not used as an alternative to cross-validation. It's used as an alternative to parameterize regularization. Okay? This is a common confusion. Okay? Then, if we agree on that, then we can compare them. And the main point here is to make the comparison on the computational level. Tikhonov, if you want to do cross-validation, you would have to solve the problem for every parameter lambda and get this complexity times this. In principle, this guy will actually allow you to just replace it with this ONPT. I'm not claiming in any way that this will be a better statistical estimator. I'm claiming that it will provide an essentially equivalent statistical estimator that can be trained and tuned at a much better complexity. And also, hopefully, it just tells you a new way to think about algorithms. Optimize something on the data and just use optimization, computation as a regularization. Make sense? Yeah, yeah. So that's another good question. It's another obvious question. So I'm always saying, you know, lambda is equal to 1 of t or something like this. Clearly, t is a discrete parameter. As lambda is a continuous parameter. Okay. For example, I can take a logarithmic discretization of lambda. Well, you cannot really do the same thing for t. Okay. There is no theoretical result. Well, it's not true. It's hard to prove a theoretical result that says what you're saying because typical results. And this stuff hides in the constant. So from the point of view of any kind of convergence you want, from a statistical point of view, from an optimization point of view, the answer is no. Okay. It's minor constant. In practice, it's going to happen only if you really have to do very few iterations. Okay? If you really have to do just very few iterations. Usually in practice, a few iterations are needed. And so this effect doesn't really show up. Also in practice, typically, this is just, you know, as it happens for lambda, the story is a bit more complicated than that, right? So you typically have some other parameters to tune. Say you have a kernel and you're using the width of the kernel. You're using a neural net number of units or something else. You have the step size and you're actually tuning them in some way. And then you will basically see that this concur in having control on what happens between iteration because you can make the problem slightly more over 50 or slightly over 50 and so control that. The first statement is very theoretical. You cannot, and I don't know if anyone knows what you're saying from a theoretical point of view because it would be getting a very sharp evaluator of constants that I've never seen. From a practical point of view, the answer is usually not. Okay. Yes.
Is this sort of intuition?
Yeah, so that's the other big question. Okay, everything I show you now is for least squares with square loss. How about other stuff? Okay, so you can go in two directions. One is to say, how about other algorithms? So keep the square. So he wants to replace the squared norm with something else. Okay, he wants to replace the square loss with something else. I want to replace the gradient descent with another algorithm because I like optimization, and this seems the dumbest choice. Okay, let's go one by one. This is a method from the 60s. Okay, what I show is not exactly new. Okay, it was reinvented under the name of L2 boosting in the machine learning literature, and then proved all this connection made clear some 10 years later. So we're talking about 90s and 2000s. The general idea of doing this trick, people use it all the time. If you look at the bag of tricks in neural networks, the third one is early stopping. Okay, early stopping is kind of a slightly confusing word because it feels like that stopping early is the main key. The key point here is that the regularization are controlling, so the iteration controls the complexity of the solution. Okay, you actually have to go all the way down. It's like taking lambdas very small. It's not about that. And the name of this is typically, the correct name is iterative regularization. Okay. the more correct name. Otherwise, you end up saying, why early? Why early? No, early nothing. Okay, early sometimes, early not sometimes. It's just iteration does the job. That's the important bit. Okay. Now, going back to the question, for loss other than del 2, it's all the works are relatively recent. You can do it. It's not as easy. There is a question, if you want, which is, how the hell this guy knows that I want to, where is the, it's pretty clear that I'm using the square laws, but how does this guy know that I want to go to, you know, that I want to control this? How does he know? Where, I mean, there is lambda equal to 0, so how does this gradient know? Okay? If I want to use another loss, penalty, how can I design an iteration? You can think about it two ways, and there are a few papers in the last 5 years doing this. One way is to say, when you write the definition of a gradient, you have to take a limit, and the limit is with respect to norms, okay, in some space. This is the definition with respect to this kind of norm, L2 norm. If you have another norm, you have to redefine the gradient using this other norm, and that's what is typically called Bregman divergence-like iterations, or if you want, mirror descent-like iterations. So you basically have to write the metric, and rather than the usual Euclidean, you have to take another one, and then you get another iteration. So that's one way to think about it. And this is just a pointer, okay? Nothing of what I said is immediately obvious. These are just the pointers. Another way you can think about it, if you know what duality is, you can actually consider the dual problem, empirical objective. You put lambda, so in some sense you have to take a dual formulation of this with any norm you want, and then just gradient descent in the dual. So again, you do gradient descent, but in the dual. These two things I just said, mirror descent with the norm you want, or gradient descent in the dual are essentially equivalent. Okay? And this gives a way to go in that direction. For anybody I'm talking about, there are papers in the last few years that do this. Okay? What about keeping this, keeping the L2 norm somewhere, okay, and just changing the loss function? Also, the case you have a bunch of ways of doing it. One way is to do subgradient. You just do the subgradient method, okay, which is a method which is slow, but in fact is low once you want to optimize this. But if you actually check, now you have a full game. If you're an optimization person, you just have a completely different game now, because you always can wonder about, typical optimization is about how to compute this guy, and now you just have a different figure of merit. Use an empirical optimization to actually solve a real problem. It's more like robust-like optimization, okay? So if you use subgradient, for example, so you change the norm and use a different loss function, it's going to be very slow at doing this, but you actually get this point pretty much. So you can generalize this to different loss functions and different norms, and then you can also mix it, and let's say you can generalize this to square loss with other norms, or squared norm with other loss, or also do the two things at the same time. Okay, so in signal processing, people love to do TV regularization, total variation regularization, or L1 regularization with Kullback-Leibler loss functions, or say learning, you might want to do L1 penalization with logistic loss. You can also do that. This stuff became popular in the last few years because, again, of this story that in somewhat you take statistical computation somewhat at the same moment. This last topic is important in large-scale learning because essentially when you have very large-scale data, you don't want to ask for a numerical precision which is beyond the purposes of your task. So if you have machine learning guy, you don't want to just run things forever when you spend 2 days just looking into noise. So in some sense, this whole story is a way to merge the requirements and the numerical requirements in the same picture. And people talk about statistical offs and try to get somewhat good ways to think about this. So let me tell you two things, okay? One, that is a calculation I'm not going to do, okay? But maybe I'll show you at least the result next time. And is, okay, everything I did here is for the linear case. Is for the finite. If I use this as an algorithm, I have to run this as a, in the feature space, in a finite dimensional feature space. Can I do a finite dimensional representation of this and use a representer like iteration? Yes. You use the same trick. you want, you basically can move this in front, sweep this, go back and see what you get, blah, blah, blah. It's 2 lines. I'm going to show it to you next time, but it's the same thing we've been doing. Okay, you just prove that this satisfies a representer theorem, and it's a very simple iteration. So everything interesting is happening here. That's, you know, hopefully what you see is that in this course, what we do is that we build some tools, and then after a while, we keep on using them. Okay, so we add some new stuff. The new stuff is this. How to go from linear to nonlinear. There's nothing new there. It's the same technique we were using now for 3 times. The other interesting bit that I would like to tell you is the last thing I mentioned before. We don't want to change the norm or the loss, but actually want to change the algorithm. And that actually is very interesting. Okay, so give me my full 3 minutes to say this. Anybody of you is familiar, you know, what's happening in optimization? People are obsessed with trying to accelerate things, right? They try to get fast solver for things. Now, I give you this perspective. You care about a fast solver or not? Let's say batch so that we can back to. I wanna do things efficiently, so I care about solving things right, but I want to solve a learning problem. So this is the picture I have in mind, okay? So I'm fine working batch, but I want to be efficient, okay? And I want to know, does it make sense to accelerate or not? Accelerate would mean what? Take this curve and shift it down, right? You take the empirical objective and you make it go down faster. Say this is GD and this is our form of acceleration. Momentum, Nesterov, whatever you want, conjugate gradient, so on and so forth. Class is not about that. It's about the one above. Okay, designing way to solve the one above. Defined in lecture 1 was not try to minimize the empirical risk as fast as you can. No, try to learn. So why would it be a good idea? Yes. Accelerating. Again, you have your friend is work with Isra, who's accelerating things every day, and you want to steal his algorithm because now you know that you can steal optimization stuff for learning. And he knows how to do this. He knows how to go from this curve to this curve. Should you steal that algorithm or not? One way is no, because you just overfit faster. Okay? My concern is that things can happen faster. That's a problem. Typically, that's not the concern. Okay? Typically, you have time to let things happen. And that's what happens is that this curve doesn't go up or down. You don't get a better solution, but you can stop earlier. Okay? So I even going to use a different color for once. So if you give me an accelerated algorithm that decreases my training error faster, the effect is that I'm actually going to get another algorithm that also is going to, go down and then up. Is not going to do anything better, okay? Generally, you cannot prove that it's better. In fact, all these algorithms can be shown to be optimal in a precise sense, but things happen earlier. So you actually can prove that you need something like the square root of the number of iterations to get the same accuracy in terms of learning, not in terms of optimization. So acceleration is good because you can do early, okay? You can somewhat use less iteration. So yes, go there and steal all the algorithm you can, just take care of maybe proving something along the way. The last comment I want to make, because I have 0 seconds, is that this is the picture where you have a lot of computational power. Suppose that this is the picture you get, okay? So your data set is so big that you're never in this regime, okay? Then the picture is somewhat different. You never stop, and you just want to go fast, because going fast is just getting the expected error to 0. So in some sense, when the data gets really, really big, oftentimes what you do is to just try to minimize error as fast as you can, because all you care about is to shift this down. So again, just try to redraw this and forget it. All right, that's it.